Hi students, in the first session we have discussed about finite element method. How finite element method works, what are the different steps involved in finite element method, what are the phases in FEM, what are the advantages and disadvantages of FEM. We have discussed about it. Hope you understand the concept behind finite element method. Finite element method is completely discretization of structure and finding unknown at the nodes. Discretization means subdividing a structure into convenient number of elements. When you consider a single element, it will have some nodes. Okay. Think about any point inside the element, that is non-nodal point. So, for that reason, we need to have an interpolation function. Let's see in a formal way what is shape function. In finite element analysis, the aim is to find the field variable at nodal points by rigorous analysis, assuming at any point inside the element, the basic variable is a function of values at the nodal points of the element. That is, the function which relates the field variable at any point within the element to the field variable of the nodal points of the element is called shape function. In more clear way, the values of field variable computed at the nodes are used to approximate values at non-nodal points by interpolation of the nodal values. This function is called shape function. It is also known as interpolation function and approximating function. Let's see a three-noded triangular element. I have mentioned the nodal points and non-nodal points. Since triangular element, there are three node points and some nodal points inside the element. So the nodes are exterior, and at any point within the element, the field variable is described by following approximate relation. This is the relation of shape function. Phi of xy is equal to n1 phi1 plus n2 phi2 plus n3 phi3, where phi1, phi2 and phi3 are the values of the field variable at the nodes, and n1, n2, n3 are the interpolation function. So this interpolation function is also called shape function because they are used to express the geometry or shape of the element. One of the main characteristics of this shape function is that it has unit value at one nodal point and zero value at other nodal points. So a single shape function will have unit value at one nodal point and zero value at other nodal points. When we consider a one-dimensional bar problem, you can write the basic field variable as displacement. When you consider two-noded bar element, consider a bar having two nodes, then the displacement at any point within the element is given by u is equal to n1 u1 plus n2 u2, where n1 and n2 are the shape function and u1 and u2 are the displacement at the nodes. Okay, so this can be written in matrix form as u is equal to n1 u1 and u1 u2 matrix. Okay, one is a row matrix and other is a column matrix. So and another characteristics of shape functions are sum of the shape function is equal to 1, and the shape functions are always polynomial of the same type as the original interpolation equation. Why polynomials? Means polynomials are quite easy for differentiation and integration process, and it is easy to formulate and computize the finite element equations. And in general, shape function should satisfy the following things. So first derivative should be finite within an element, and displacement should be continuous across element boundary. These are shape functions characteristics. And one more, the shape function for two-dimensional elements are 0 along each side that the nodes does not touches. Okay, so this is the basic of shape function. So for a two-noded bar element, the shape function equation will be u is equal to n1 u1 plus n2 u2. Here for one-dimensional bar problem, basic field variable will be displacement. So let's see derivation of the displacement function u and shape function n for a one-dimensional bar element. You can see that a one-dimensional bar element having two nodes 1 and 2, the bar length is L, and u1 and u2 are the respective displacement at node 1 and 2. Since the element has 2 degrees of freedom, it will have two generalized coordinates. Okay, so you can write u is equal to a0 plus a1x generally. So a0 and a1 are the global or generalized coordinates. We can write it in a matrix form. U is equal to column matrix of 1x and matrix of 1x and matrix of a0 a1. You can write it like that. So after writing like that, we will apply the boundary condition. At node 1, you can see u is equal to u1 and x is equal to 0. At node 2, boundary condition is that u is equal to u2 and x is equal to L. Why x is equal to L? Because x is the the total length of the bar element. So substituting the above values in equation 1, u is equal to a0 plus a1x, we will substitute these boundary conditions over there and we will write in matrix form. We will write it in a matrix form. So u1, u2, it's a column matrix, is equal to one row matrix into another column matrix. 110 L is a row matrix and other is a column matrix. So rearranging for a0 a1, you can get the equation like this. One column matrix and other one is a row matrix. So row matrix is inverse. So there is an equation to note. Matrix of a11, a12, a21, a22 elements, inverse is equal to 1 by a11, a22 minus a12, a21 into matrix of a22 minus a12 minus a21 minus a11. Applying this equation, we will get, and we can reduce it to the equation a0 a1 is equal to 1 by L minus 0 into the matrix into the column matrix. Substituting this value of a0 and a1 in equation 2, that is the matrix form equation 2, and when we reduce that equation, we will get u is equal to matrix L minus x by L is as one element and x by L as the other element, and the other column matrix u1 and u2. So we can say that the displacement function for a two-noded one-dimensional bar element is u is equal to n1 u1 plus n2 u2, where shape function n1 is L minus x by L and n2 is x by L. This is the derivation for one-dimensional bar element. One-dimensional bar element, displacement function and shape function. So let's see a simple problem related to this shape function. Consider a two-noded bar element. The nodal displacement is u1 5 mm and u2 is 8 mm. calculate the displacement at x is equal to L by 4, L by 3 and L by 2. So there are two nodes 1 and 2. Respective displacement are u1 and u2. The field variable at the nodes are u1 and u2. So we have to find the displacement at non-nodal points L by 4, L by 3, L by 2. Okay. So we will use the equation u is equal to n1 u1 plus n2 u2. And we know that n1 is 1 minus x by L and n2 is x by L. Simply substituting the x value, u value, u1 and u2 value, you will get the answer. At for one example, at x is equal to L by 4, we will substitute u1 is equal to 5 and u2 is equal to 8. Then u is equal to n1 u1 plus n2 u2. We will directly get the answer as u is equal to 5.75. Similarly, for x is equal to L by 3 and similarly to x is equal to L by 2. These type of simple problems may ask for 2 to 3 marks. Okay. And when we consider higher order element, that is for one dimensional bar problem only, one dimensional problem, higher order quadratic element, we can write u is equal to a0 plus a1x plus a2x square. So the displacement function will be u is equal to n1 u1 plus n2 u2 plus n3 u3. As we discussed in a similar way, you can derive it and you will get that n1, n2 and n3 values. That is n1, n2, n3 are the shape function and u1, u2, u3 are the field variable, that is displacement at 3 nodes. Okay. Hope you all understand what is shape function, what are the characteristics of shape function and how to derive the shape function for one dimensional bar element and a problem related to this shape function. This is a simple topic. You all should study this topic. The next topic we will be discussing is stiffness matrix in the next section. Thank you.